Today I will finish bridges and then we'll handle the temperature sensors. Last week I showed you some basic properties of AC bridges. We've been talking about the one-water bridge. So how many sensors are there in the one-water bridge? If I have 4 resistors in a bridge, if I say it's a one-water bridge configuration, how many sensors are there and how many fixed resistors? How many? 1? Yes, exactly. So we have 4 resistors in the bridge and only one of them is the sensor itself. And we concluded that the one-water bridge has some sensitivity. This sensitivity tells us how is the output voltage or current changing if you change the resistor inside the bridge. And we concluded that the sensitivity of the one-water bridge is 1 compared to the other types of bridge that we will be talking now. So remember that the one-water bridge has a sensitivity of 1. We've been also talking about the linearity of the bridge and the influence of the internal resistance of the voltmeter. So we know that the more low the bridge output voltage, the more the voltage drops and the more linear it gets. So we can see here what is the output voltage as a function of imbalance of the bridge. This is the output voltage, and here we see 3 cases for various values of internal resistance of the voltmeter. So the blue line is the same case that we have found in the class. It's a voltmeter with an input resistance of 1.2 kilo ohms, and you see that there is a significant drop in the voltage compared to the cases where you have more internal resistance in the voltmeter. So for the bridge, it's really important to have as high as possible the internal resistance of the voltmeter, because then you have high output voltage and high sensitivity. But in all cases, you see that the voltage is non-linear. So if I use unbalanced bridge, we have to take this into account, and we have to work only in a very small area around the origin. There we can say there is small error, 5% to bridge normal steam. And we've seen also this graph that is showing us the imbalance of the bridge 2%, and just by considering or not considering the nonlinearities, we have got 1%. So it's really important to be just close to the balance point of resistance of the bridge. And the second configuration is using 2 sensors. When one-water bridge has 1 sensor, it has sensitivity 1, then how do I improve sensitivity? I can choose 2 sensors. So I can install 2 sensors in the bridge. So for example, here and here, we remember the condition of balance is always this, and then equals this and this. So in this case, those 2 resistors are either fixed. In the case of an unbalanced bridge, we measure directly the voltage, or we can have those resistors variable, and we can try to balance the bridge and achieve voltage 0. In the case of 1/2 bridge, you have 2 options. You can have either the sensors that change in the same direction, the change of the input value. It means, for example, if this is a temperature sensor, I increase temperature, resistance will increase. So in this case, in order to unbalance the bridge more with the change of the input value, you install the sensors in this branch of the bridge or in this branch. In a way, the same side of the balance condition. So this is meant by the two sensors with the same sign change. This is typically used, for example, for force sensors. When you want to weigh something, measure torque, then you typically use 2 or even 4 sensors in range configuration, and then this would mean that the 2 strain gauge sensors, force sensors, would both measure tension or compression. So they have to change with the same change of the value. The second configuration is when the sensors behave differently. For example, if you temperature, one sensor is increasing when you go distance, second sensor is decreasing when you go distance. Or again, typical case, 4 sensors, one sensor will measure tension, the second sensor will measure compression. They are both cases by the same force, but on a beam, for example, but on the beam sides they will act differently. So one will be compression, one will be tension. And in this case, if you look at the condition of balance, if I have those kinds of sensors, I want to unbalance the bridge, so I have to install the sensors in this one. Here, or here, or here, or here. So this is the second configuration. We can also make the analysis of sensitivity, and we will come to the conclusion that it looks exactly the same like for the one-quarter bridge, except that for the one-quarter bridge you get 1 and 1, but for the one-half bridge we get 2. So the one-half bridge has double the sensitivity of the one-quarter bridge for the cost of one additional sensor. For sensors, this is quite a typical configuration to use either a one-arm bridge or a full bridge. Because we want high sensitivity, we will see also other advantages of this configuration later. So remember that one-arm bridge doubles the sensitivity of the action. Do I have any options to increase more sensitivity? Okay, yes. So we can use a full bridge. So the full bridge configuration is the same schematics, but here we use 4 sensors. But in this case, we see that 2 sensors have to change in the same direction to the input value, and 2 sensors have to change in the opposite direction. Again, the example for 4 sensors, I have beam embedded, so 2 strain gauges installed in the beam will have to measure compression and 2 will have to measure tension. This is noted by the signs in plus and minus, so this is one direction here, this branch of the bridge, and the second branch is there. For this case, there is no other option. You have to always install them like that, so you unbalance the bridge. So here we can make the analysis about the sensitivity, and we will come to the conclusion that here in the form. So the full bridge configuration doubles the sensitivity of the one-arm bridge configuration, and compare one more bridge, the sensitivity is 4 times bigger. So that's the advantage. The disadvantage, of course, is that you have to install 4 sensors, but for those sensors where DC connection is typically used, it's not usually a problem of cost, because the sensors themselves are quite cheap. The installation has to be electronic and expensive. So the sensor costs I don't know how much it runs, so it's not only for it. And you gain more precision, more sensitivity, plus you gain the advantage of temperature modulation, as we're talking about this in more detail in forces. So this is everything for AC bridges. For AC bridges, it will be the same conclusion. We can have one-quarter bridge, we can have one-half bridge, we can have full bridges. So we'll be not talking about the equations. I'll just show you something, some schematics and some short information. So AC bridge. The difference is the power supply voltage. It's powered with AC voltage or AC current, and we will use the AC bridge in case where the sensor changes what value in the circuit. Let's say if I will have electrical resistance, capacity, or inductivity. So for those three cases, which type of bridge do I choose? I have, let's say the input is change of electrical resistance, or change of inductivity, or change of capacity. And output is voltage or current. So my question is, what kind of bridge do I use for those three cases? So let's say we have electrical resistance, we have capacity, and inductivity. This is the output value of the sensor. So what type of bridge do I use for those three? AC or DC? AC. For which ones? So capacity and inductivity. Okay, so here I will have to use AC, and here I will use DC. It's true that I could use AC bridge resistance changes, but it's not very convenient because in the circuit itself, we then have additional capacities and activities that would add some noise and some controls. So typically, if my sensor is changing electrical resistance, I'm using DC bridge. If it's changing capacity or activity, I'm using DC bridge. And in the AC bridge configuration, now it works exactly the same like in the DC bridge. The only difference is that we don't have resistance, but we have impedance. So if you look at this schematic, it's exactly the same configuration. I have a power supply, AC power supply with some resistance. I have 4 impedances to the bridge. Here's Z1, 2, 3, 4. And the balance condition is also the same form. So it has Z1, this element times Z4 equals Z2 Z3. So this is exactly the same condition. Now, as we have impedance, an impedance has 2 parts. It has a real part and an imaginary part. So it's a complex number. So in order to balance the bridge, for an AC bridge, we need 2 balancing elements because we need to match the impedances and the phase shifts. So we will have 2 balancing elements, which gives us the option of one order bridge configuration. So let's say this would be the sensor, and we need 2 balancing elements in the bridge to achieve 0 voltage on the output. So this is that typically the limits of circuit balances automatically, or some noise. The sensitivity again will be balanced.
What do you mean exactly is complex? Values
Yes. That value is composed of some real power plus J and X. So this is the real power of the impedance, and this is the impedance. So this is hidden under this Z, and then if you have those 2 conditions, you need to balance the real parts and the complex parts. So you need 2 elements. So this is AC bridge. And our last configuration would be a differential bridge. One group saw that already on class. The configuration is very similar to the arrangement of all the bridges we saw here. So we have 2 power supply voltages, AC, and 2 impedances. In general case, we have 2 resistors in the line. And again, the balance condition is this voltage times this impedance equals this voltage and this impedance. When it's 0, then here the output voltage will be same as well. The typical use of this differential bridge is position sensor. Where we will be talking about position sensor. After this is an RTD transformer, and we will see more in detail what is inside this device. Again, this is the sensitivity. Change of current as change of impedance. So that's the differential section. Any questions so far? Okay. So when you have this output voltage from any kind of bridge, so although it acts as an amplifier, so it takes a small change in the input value from the sensor, gives you a little bit bigger output voltage or current. Even if it acts like that, then the voltage on the output terminals is relatively small. When we done the experiments, we saw okay, 1 volt, but we had a relatively big imbalance. So typically, this stays in an order of some millivolts. So still, the voltage is quite small. So we need a way to amplify the output signal even from the bridge if you transfer it to some visual instrument. And one way how we can do that is to use a difference amplifier. You know what this symbol is? This symbol. Yes, okay. So this is an operation amplifier, and it amplifies the voltage difference between the inverting and non-inverting terminal. And if you use this connection, so we have here the negative feedback and 4 resistors, then we go to the conclusion that this connection amplifies the voltage difference between the inverting and non-inverting terminal inputs. So this acts as an amplifier. You need to remember any of those equations. Just remember that such connection exists. That we have some difference amplifier. And we can see that the amplification of this voltage and that voltage depends on the values of the resistances that we use in the connection. That's logical. And if I simplify the connection, I come to this final conclusion. So if I assume that there is a given ratio between the resistors inside the connection, then I have such a simple equation that the voltage difference between this terminal and the terminal is on the output, and it's times the amplification given by the resistor R2 and R1. So we amplify the voltage difference. It is of course possible to use just simple schematics, but we will have typical problems with operation amplifiers. There will be offsets, there will be changes with temperature, and so on. So this is the very simple schematic, but in reality it wouldn't work in, let's say, industrial environments. So we are talking about this difference amplifier only to know that there are integrated circuits that already have this connection inside, and that you can buy them. It's not that expensive, and you can directly use them to bridge output or any kind of sensor output. This connection is, this circuit is called an instrumentation amplifier. So the chip looks like that, has typically pins, and what is inside is this kind of connection. Here you see the difference amplifier. It's exactly the schematic I showed you. Here we have one operation amplifier, 4 resistors. This part of the connection here amplifies the voltage difference. One of the problems of this connection when it's used directly is the difference between the input resistance of this connection and that connection. I go a little bit back to sees the resistor R3 plus R4. So those two R3 and R4 are in series. This is typically a small value, let's say 10 to 50 kilo ohms, so small value. In this connection, it is only R1, and then the input value, the input resistor of this is very high. So on this pin, it is a very high input resistance. And that's a problem, because we have different loads for the two signals. The bridge is very happy when it's loaded the same way on both pins. So there is a different resistance here, different resistance. That's the problem with this single connection. For this reason, in this connection, there is an additional operation amplifier. There are two of them, one here and second here. You can see that they are connected in exactly the same way. The input voltage goes always directly to the non-converting input. And there is a negative feedback. Here, for this input is the same. Voltage to the non-converting input and feedback. So this is typically always some electric resistance. So these two operation amplifiers, they act like buffers. They have a very small amplification. They are there in connection just to modify the impedance that the input circuit is seeing. So it sees typically a very high input resistance, because this is very high values, ohms, and then the amplification of this whole instrumentation amplifier is changed only by changing a single value of this resistor. So all these operation amplifiers, all these resistors are hidden down inside the chip, and here you have only two terminals, RG here and here, where you connect one resistor that will change the amplification. So this is a ready connection, ready circuit, needs just one resistor on the input to change the amplification. And it works quite well with bridges and if you want to amplify any kind of signal. Any questions?
Back so I can get the diagram.
This one.
Yeah, I've got it. It's back.
Yeah,
It's okay. Thank you.
good. So this is all about circuits. Now we'll go to the real topic of architecture, which should be temperature sensors. And we'll use again for the bridges and we'll go over that. Before we go to the sensors themselves, one question. What is temperature? If I say temperature, here is a degree centigrade. What does it mean? What? Measurement. It's quite difficult to define if we just ask this question, what is temperature? I don't know. So, yeah. So we can use definition based on temperature. So what is the amount of energy movement of atoms in the air, for example? In order to define the temperature a bit more precisely, there is something that's called an international temperature scale. And this international temperature scale, ITS 90 because it was accepted in 1990, defines us some points where we can say, okay, now we know precisely what the temperature is. Typically, this international temperature scale defines us temperatures in a very broad range. So from about 0.65 kelvins up to a temperature that is measurable with radiation using Planck's law. So it goes from very small temperatures up to very high temperatures. And within this range, we have some see an example of this international temperature scale here. Typically, these fixed points are defined as triple points of some substance or as boiling points of some other substances. So one very important point that we will use to define temperature is this one, 0.01 centigrades. It's 173.60 Kelvin, and it's a triple point of water. You can see there are different kinds of definition points. For example, here triple point of mercury, 234 and something kelvins. So this is how you can precisely define what the temperature is. I have here a table just summarizing the temperature and the triple points. So this will be the most important for us. 273.60 triple point of water. The other are just an example. For example, this one, freezing point of carbon. And if you want to standard and calibrate your sensor, and you have to bring the sensor to a lab, already have some way to obtain those points and define temperature. For us, it will be important that approximately between this temperature, between approximately 660 centigrades and minus 250 centigrades, this temperature can be measured with a platinum thermometer. So the first and the most important thermometer we will be talking about will be the platinum sensor. The platinum sensor works by changing the electrical resistance as a function of temperature. We will also see that no single platinum sensor can be used in this huge range from minus 250 to 660 centigrade. It's a big range, and we can use that in a smaller range when we don't use it precisely. So if you buy a platinum sensor, it will be calibrated in some range, and in this range you will have some data about its accuracy. If you want some other range, you have to recalibrate it, because we will see that the platinum sensor is non-linear. So even if we use all correction coefficients, we will have some problems with accuracy in this range. So the first type of sensor that we will be talking about is the platinum sensor. All metals and also semiconductors change their electrical resistance to temperature. Those type of sensors are called RTDs, resistance temperature detectors. So if you look for some data on the internet about this kind of sensor, then look for an RTD. In a smaller temperature range, we can typically define something that's called a temperature coefficient of resistance. In other words, the temperature coefficient of resistance tells us how is the electrical resistance changing if I change temperature from 0 to 100 centigrades. So between 100 centigrades and 0 centigrades, I define what is the change of electrical resistance. And this is the here. So the temperature coefficient of resistance alpha is the difference between resistance from 100 minus resistance 0, and it's related to alpha. It is, you can call it sensitivity. So in this smaller temperature ranges, let's say plus minus 100 centigrades, we will have a relatively simple relation between temperature and between the electrical resistance. So we'll have something like the electrical this works quite well in small ranges. But if you want to use the sensor for some higher ranges, let's say from 0 to 500 centigrade, you will find out that you need something more complicated, because the accuracy of this simple equation will not be sufficient to describe the reality. And we can use this form of the equation. You can see that it has a similar form. There is 3, there is 0, 1 plus 18. So only this part would be the same as the simple form. But then we have different coefficients. We have B, and we have C, and we have some powers of temperature. So for smaller values of temperature, we can say, okay, this will be small, that will be small, and we can just answer this part. For higher ranges, even though the coefficients B and C will be very small, they can become more significant. So if you want to use RTDs in a higher temperature range, then you need to use this form of equation. And the temperature scale defined by ITS 90 defines you also this value of the coefficients of the different resistance sensors. So you have to take a look at the tables and read what is the value of those coefficients if you want to use them. So here, just to give you an idea of the magnitude of the temperature coefficient of resistance. So here is alpha as the temperature coefficient of resistance. Here are 3 different metals that are used for RTDs. The most common is platinum. We will also talk about nickel and copper. And the third column here is resistivity. So it means if I have a wire with 1 meter length, with 1 millimeter cross section, what will be its electrical resistance? So let's compare the first values. Platinum has about 3.92. This is nothing particular. And then nickel has about double the temperature coefficient of resistance. This means, of course, it's also sensitivity. So if I change the value of temperature, I will have some output electrical resistance. So just for this table, it would look like that nickel would be a better metal for RTDs because it has about double the sensitivity. We will see that there will be more problems with nickel and platinum. So I will tell you that platinum is great, it's expensive. So if you want something cheap and buy nickel, you will have more problems. Also, copper. Copper has approximately the same sensitivity like platinum, but we will see even more problems than with nickel. So if you want something really cheap, you can use copper sensor, but it will last really for a short time. And then, if we compare this last part, the resistivity, we will see that approximately platinum and nickel have the same value. It means that the wire of the same length from nickel and platinum, and of course the same diameter, will have approximately the same electrical resistance. But copper with the same length and diameter will have much lower electrical resistance, which will mean that if I were to build a sensor with, for example, 100 ohms, then I would need 10 times the lower copper wire, which would be very convenient to be a problem to fit it inside the housing business. So copper is not very good for this reason. Platinum and nickel have relatively high electrical resistance, which will give me a smaller sensor and will fit inside the housing. So now let's take a look on the properties of the platinum sensor. The big advantage of the platinum is that it's very stable. It's used in applications things, jewelry, for example, electronics, and so on. Another reason why we use platinum for sensors is that it has high electrical resistance. It means that I will have small current in the circuit, and it will reduce me self-heating resistance. Because if I have a resistor, I have a current flow through this resistor. There is always some heat produced the current, so choke losses. So this is an advantage of the platinum sensor. But maybe the biggest advantage of the platinum sensor is that it can be exchanged in the application without calibrating the sensor. Because platinum is stable, it's precise to produce the real the good size of the electrical resistance. We can say, okay, I have platinum sensor. If I need to measure the temperature in my application, then a little bit later, for some reason, I need to exchange the sensor for mechanical imaging, for example. And I just take the same type of sensor, place it in the application, and I don't need to recalibrate the whole work. So that is the biggest advantage of this platinum sensor. For those three reasons, the platinum sensor is the most common type of sensor used for temperature measurement, although it's expensive. And there are several types. It's always called PT. So this PT means that it's platinum, and the number means what is the electrical resistance for 0 centimeters. So if it's PT 100, it means that it has precisely 100 ohms for temperature 0 centimeters. And PT 100 is the most common temperature sensor used today. The second variety that we can find is PT 1000, and obviously it is 1000 ohms for 0 centimeters. So now let's take a look at the properties of this kind of sensor. Here you can see the equation relating temperature and electrical resistance. So we can see the coefficients A, B, C, and here you can see the values. We can see that the coefficients B and C are negative, and they are about 5 orders of magnitude smaller than the coefficient A. So if you have small temperature difference, then you can really neglect this B and C coefficient, because if you have here small temperature, then power delta is low. So it's will be very small. So within a small temperature range from about 100 centigrade, you can just use the coefficient A and use just this part of the equation, which is here, and you can say sensitivity of PT100 sensor is 0.39 ohms per centigrade, which is this value. In a bigger range of temperatures, you can even see that on the chart of this one here. So if you look on this chart, you have minus 200 to about 800 centigrade. You can see that it's a little bit, you can see it's not a straight line. So if you want to use the sensor in this whole range, you need to consider all those three conditions. And now, something about the sensor itself. I have one here. There. So I'll be talking about sensor platinum sensor. So it's a stable platinum market. If you are interested in accuracy of the sensor, there are two accuracy classes that are defined for this kind of sensor. It's called class A and class B. You don't need to remember these numbers. Just to give you an idea what is the accuracy of for 100 centigrades, this accuracy class gives you something about 0.35 centigrades. So compared to that, it's very precise. Even if you have 600 centigrades, then for class A accuracy, you have plus minus 1.35 centigrades. In ohms, it gives you a very small value. This is plus minus ohms compared to the basic value of 100 ohms. So if you have 100 centigrades, then you have plus minus 0.13 ohms. So again, you need to measure the electric resistance very precise. However, it's not so easy. We have class A, class B. Both sensors, both classes are produced from a very pure platinum. When you buy such kind of sensor, you need to be aware that there is a difference between the, say, European standard and between the American standards. So it's all different standards. And you can't really buy a sensor that is made on the other standard. Why? Because there is a difference in the purity of platinum. And it will give you a difference in temperature reading. And it's not so insignificant. Let's take a look at this chart. This chart shows us the difference between the American and European standards related to temperature and the temperature that we read on the hour. So for 0 centigrade, it's okay. All those standards have precisely 100 ohms for 100 for 0 centigrade. So the temperature difference between those two standards is good. When you go down, here you have minus 100 centigrade, and the difference in standard is about 4 centigrade. So it's quite big. This is 4% error, and the accuracy class defined here will give you about 0.35% error. So it's really important to know that. For higher temperatures, it even worse. So let's imagine I want to measure something really precisely, 500 centigrade, somewhere here, and I have about 9 centigrade error. So then it's a quite huge error. So when you use this kind of sensor, it's not only important to know what type of sensor you want to buy, but also what standards we use in your application. I don't think it really matters if you use that standard or the standard, but you have to use the same if you don't need to calibrate your application. And now, what is inside the sensor? Here, I'm showing you the version of glass EP100. So it's a glass encasing, and inside this glass encasing, there is a thin wire from platinum. Typically, it's made in the way it's called full winding. We know what it is. Yes? So it's a special form of winding that reduces inactivity. Because the current goes this way, all the way, and the two wires are always in the current. So if I have a current flowing here and there, and then back, it's always in the current. So it reduces inactivity. Typically, just this sensor costs between 50 and 100 euros a piece. So it's quite expensive. The temperature range that you can use for this is typically about 600 centigrades max. Then you have problems with this glass encasing starts to melt, and so on. So this is about sensitive environment. Still works. So that's the glass PE100. It's clear that I can't take this sensor directly and place them into some industrial process. It's too fragile. So we then need to place that well well that at the end you place the sensor inside, seal it, and then this is in the application. It's protected. You can remove the sensor without interrupting the process. If you have a good contact with the sensor and the terminal, you have a quick transfer and you will have a small time install. So we'll also make some experiments with that. What happens if I have such kind of terminal or such kind of terminal? It's clear the time constant is really smaller. Those are an example of some terminals. So this is the glass ET100.
See, what is the purpose of glass?
The problem?
The purpose of the glass.
To protect the platinum wire, to mechanically hold it.
But it's inductive to heat, so it will not cause a problem.
It will not cause a problem if the temperature is over 600 centigrades. If it's higher, then it can break and so on. There is another problem of this version. The glass encases completely the platinum wire, and the thermal expansion of the platinum is different from the thermal expansion of the glass. So there will be something that is called a strain gauge effect. It will also limit us this temperature range. It means that we will stretch the wire and we will change its electrical resistance. So those are the problems of the platinum wire encasing glass. Glass is really fragile, but it's less expensive to produce that with glass than to do with some other materials. It doesn't have to be always that big, so we can have, let's say, 4 centimeters of sensor. You can have longer sensors if you want, but you can also have smaller sensors. But in all cases, you need to protect them quite well and place them in the home. The second version of the PT100 is encased in ceramics. So it's a ceramic PT100. The principle is the same. It is thin platinum wire, typically diameter 0.05 millimeters, very thin. And this wound and placed inside the ceramic casing. The difference between the ceramic casing and the glass casing is that the glass casing is completely covered with the glass. For ceramics, we have 2 holes, and the wire is placed coil inside. So it's free to move inside. So for this version, we don't have such a problem with the strain gauge effect. Even if the coefficient of thermal expansion of the ceramics and the platinum wire is different, it doesn't have to be. Because if I change this temperature, it will expand, this will expand. The platinum wire is free to move inside the holes, so we can move out of the holes. Plus, the temperature resistivity of the ceramics is better than for glass, so we can hold for higher temperatures. So typically, this platinum ceramic sensor can work up to 850 centigrades. So a little bit more than the glass version. The price is approximately the same. Yes. So you will have different diamonds. Again, you need to place that in a terminal. So I have some examples of some bigger terminals here. So I have a terminal like that. I have a terminal like that. Or you can have something like this. So it really depends on your application. What do you need? You need a long one, short one. The sensor itself is then placed in such thing, and this inside the terminal. So there are in fact two terminals inside. You need to have a good contact. When you have metal, it will have a shorter time constant because the heat transfer is better than the ceramic one. But if you need some chemical resistance for acid, for example, then you can't use such a simple terminal as you use ceramic ones. You can have smaller terminals again. This is also a big example. Not all those sensors and terminals actually need RTD ones. Some of them are examples, but you can use the same terminals. Here, you see a smaller and have really small terminals. So it can be some small application, if you're not very robust, you can have to use small terminal. Okay, here's the ceramic version of the sensor. The last version, where you are really limited in space, is the thin film version. The thin film version also uses platinum, but in this time the platinum is not in the form of wire, but is in the form of paste. So you have a curved border like that, substrate, and there is a thick track of platinum. The advantage of this arrangement is that it uses very little platinum, so it's less expensive than the fire materials. It's very small. In German example, this is 10 by 2 millimeters, so it's very small. On the other hand, the accuracy of this kind of sensor is not so good as for the wire sensors. So it's less expensive and less precise. Typically, it can also work for temperatures up to 600 centigrades. And it can be really small. For example, this is 1000 into that, and it's about 200 millimeters. The price typically is about 5 times lower than for the BT one. So here are additional examples, sizes, it is bigger than the reality and the prices as well. So here I have more here. This is the last. This is a small mobile, and you see this case it is 3 virus. We also do connections. So this has 3 virus, typically 4 virus.
What does it mean?
Interrupted. Well, all those sensors were used, and they are typically not working anymore.
Do you have to put thin film ones into a thermal?
Which one?
Thin film.
No. The thin film is typically used to measure surface temperature. So if you want to measure temperature distribution and so on, you glue that on the object. So typically, this is not place than
This is copper or something.
It's what?
This is copper.
This is steel.
Steel.
Yes.
We put in like this in one section.
Yes. I'll be talking about placement next week. This is going to show you an example of the placement of the
I just want to ask that the heat interaction will take place through this surface.
Yes.
So steel is a good conductor of heat.
Not really. Copper is much better. the chemical properties are better for steel, corrosion resistance. So we typically use nickel curators. I haven't seen that always. So my questions to BD100. Okay, so then we'll talk about nickel sensors. Then the advantage of platinum is that it's precise. You can exchange that easily in the application, but platinum is really expensive. So if you want to reduce the cost and you are satisfied with some limited accuracy, you can use nickel as well. Where you need cheap sensors? Well, in applications where you need to produce many of those sensors. In an industrial application, you want that the sensor is precise, reliable, and cost is also important, but not so important as the reliability and precision. For different kinds of applications, like for example, household temperature controllers, you can't use platinum sensors. Imagine that if you would like to control temperature in this room, you have to buy a PT sensor for 100 euros. No one would buy such a controller. So even if it's I think one would buy such a sensor. So for applications where you are satisfied with low precision, you can use it. To give you an idea, a typical household temperature controller needs an accuracy of about 1 centimeter. There is no reason why you need to control temperature in your soup and to measure that when you point 1 centimeter. It doesn't make any sense. So for those applications, it's quite normal to use cheaper sensors. The advantage of nickel, as we saw in the table, is that it has double sensitivity than for platinum sensors. So in other words, it will give us higher change of electrical resistance. This will give us higher change of voltage and temperature, for example. So what are the disadvantages? So that disadvantage is here. If you take a look at the equation that describes the linearity or non-linearity of nickel, you will see that it's really nonlinear. So if you are within small temperature ranges, it's quite okay to use nickel. This is the case for temperature controllers in the room. In a room, you need to control temperature between, let's say, 10 centigrades and 25. That's all that you need. You don't need to go to 600 centigrades to minus 150. So if you are within a small range, okay, it's quite good to use such for application. And there are two class for accuracies, class A and class B. If you would compare those values with nickel and platinum, you can see that it's approximately double. So it's less precise to use nickel sensors. Usually we use nickel sensors only up to about 200 centimeters. Nothing more. The typical sensor is NI 120. So in this case, 120 ohms or 0 centigrades. You can see how the sensor looks like. This is the test version. I don't have any nickel sensors here that I can show you, so just this picture. And this chart, we can compare the sensitivities between platinum and between nickel and copper, which is great. Now there is scale is in Fahrenheit. So somewhere around here, it's 1 centimeters. As soon as I did in Fahrenheit, so nickel, in this case, they assume that it's real. You know, it's so in this case, nickel, this line, is double the sensitivity compared to the platinum. For PT1, it would be 51. So it's let's say 5 times less expensive. Typical use, typical look, and then again, sensor in the femoral for protection. If it's a room controller, then it's just a box out there, a thin film version of which is inserted inside the box. It's even less expensive. So this is the typical application for a sensor. And the third metal that we'll be talking about is copper. Copper is even less expensive than nickel. So the copper sensors will be really cheap. But copper is really unstable. Have you seen some copper roof or copper statue? How does it look like? Green, white, green. Yes, it reacts with the air, and the green is the oxidation green. So this will happen also with the pure copper sensor. So the use of copper sensor is really limited in time. You can use that for some short-term experiments. If you want to measure temperature within 1 day, 1 week. If you want to use the application longer, then you can't use copper sensors. Another disadvantage of this copper sensor is that copper has really low electrical resistance compared to platinum and nickel. So the sensor, if I would like to have 100 ohms, will be 10 times bigger than the platinum sensor. For this reason, the standard sensor is C10. So 10 ohms, in this case for 25 centigrades. I was wondering why 25, I don't know. It's 25. How we start standard device that. And it looks like this. A typical application where you use such kind of sensor is in electrical machines, where you take this sensor, you put that into the stator winding of the electrical machine, and you measure what is the temperature of the machine. So that's a typical application. Here you can see how the electrical resistance is changing. So we have 25 centigrades here, 10 ohms, and it's quite well linear. So linearity is fine, but the problem is stability and low electrical resistance. Questions so far? Okay, so now we will then go to metallic RTDs, and we'll talk about semiconductors. Semiconductors also change electrical resistance with temperature. We'll have two kinds of semiconductor sensors. One will be PTC and one will be NTC. NTC means negative temperature condition, and it means that the electrical resistance will decrease with increasing temperature. This will be the difference between the NTCs and between the RTDs. RTD is increasing electrical resistance with temperature, but NTC resistor will decrease its electrical resistance. Here you see typical examples of the steady state characteristic. So this in this case is an exponential. So it's really linear. The second thermistor type is called PDC. This means positive temperature coefficient. So it should increase electrical resistance with increasing temperature. But if you take a look on this steady state characteristic, first it decreases resistance and then increases. So this PDC is not a good temperature sensor. Because if I measure electrical resistance, I don't know, do I have this temperature or do I have this temperature? So PDCs are not used as temperature sensors, typically used as temperature fuses. So they do that, let's say here, 25, whatever ambient temperature you want, and if the temperature will increase, it will increase resistivity and eventually interrupt the circuit. So typically used with PTC is it's called return resettable fuses, and it's a fuse that if you heat it out, it interrupts. If you cool it down, it connects back to circuit. So we'll be talking only about NDCs because NDCs can be used as temperature sensors. And we will analyze this form of the steady state characteristic. We'll see if it will cause us many problems that this kind of sensor is non-linear. But it will also have some advantages. One advantage will be that its sensitivity is much bigger than the sensitivity of the platinum or nickel RTDs. Because here if you look on the slope, which in fact sensitivity is really big. So we'll have a sensitive sensor. It will be a cheap sensor, but it will be a non-linear sensor. So let's take a look at this equation describing this form of characteristic. If you look on some description, you will find such an equation. And here this is just an approximation of the reality. So we can say that the electrical resistance which we want on the output of the sensor is some natural logarithm and then an inverse value of temperature. So now I want to analyze this equation. So what will happen if I express resistivity from this equation? We'll have a really complicated result. So this is the result which you don't need to know. Only know this thing. The function between resistivity and temperature is exponential. And even this is a simplification. So if you rotate in a chart, you will have something like that. This is a typical value for a 20 kilo resistor for 25 centigrades. So for 25 centigrades, it has 20,000 ohms. For let's say minus 40, it has about 800,000 ohms. So the sensitivity is really big. But on the shape here, it's only typically the resistor sensor is used only in a small range. Because if you use it in a small range, then it's more or less in looks like it. And another advantage is that if it's changing, like so big, electrical resistance, we will not need any bridge connection. So we will have a little bit simple electronics because we will need to amplify. So if you simplify the equation, you will get form like that. So it's an exponential function. It's the only thing that you need to remember. If you want to really use such a thermistor sensor, you typically have to use some microcontroller. So you measure some values of electrical resistance. You store them in a table, so let's say 20, 30, and so on centigrades. You know what the value of the resistance should be. And you need to use some form of table inside the CPU. So although the sensor itself will be really expensive, the electronic will be more expensive than the P200. So practically, there always needs to a table. You can use also some electrical connection to make it appear more linear in some limited range, but it works really in the range. So the best way is to use some forward to stop down. How does it look like? The thermistor here. So this is a thermistor, a small bead at the end. Then this is a thermistor as well. Those are some more tabs. Again, it has to be placed in the way for protection. So typically, then it looks like this. This is a thermistor. The diameter of the thermistor depends on the application. Typically, it's between 1 to 3 millimeters. It's a small ball of material. It's placed in the thermal. In my case, it's in the glass thermal. It looks like that. So all those actually are broken. You will see the working ones on the glass. But at the end, there should be a small ball of something here. So it's really easy to produce. It's really not expensive. It's fragile and lasts a little. So now let's compare the industrial and semi-industrial version. The problem of this semiconductor material, or all semiconductor materials, is that they are destroyed with high temperatures. If you have a computer, you need to cool it down. That's why you have a fan inside. If it gets really hot, then it could be destroyed. So the same is true for the semiconductor temperature sensors, so for thermistors. The typical range where you can use it is between -85 to 50 centigrades. You can't really use higher temperatures. So if you are satisfied with this temperature range, okay, it's quite a good solution. Typical accuracy and prices here. The typical price is about the same like for the nickel sensors. And the typical accuracy is also about the same. So let's say 0.4 centigrades within range of 5 centigrades. This is the industrial version also pricing. You can also use this for your, say, homemade applications. So if you want to measure temperature somewhere, you don't need to buy such, let's say, expensive industrial version sensor. To give you an idea, this sensor is really cheap. Here I have an example of, say, the non-industrial version. It has approximately the same range, -40 centigrades. Looks like this, like 2 by 2 millimeters. Price is about 8 Czech crowns. So it's really not expensive. So if you want to buy some temperature sensor for a room, then the best solution is to use the thermistor. To give you an idea of the speed of this device, the time constant of that sensor in oil is about 1.2 seconds. So we know what it means. It's quite fast, the sensor, without that more, of course. Now the accuracy is not so good. So typical accuracy, I would say, plus minus 10%. So if you have a really cheap thermometer, uses thermistor, it shows you 20.1 centigrades. It's just some number. Plus, the error is dependent on temperature. So this value is valid only for the temperature it's calibrated, but it's increasing the error. So why don't we use thermistors for our applications? Why do we have feeding magnets? You find some reason? That's one reason, yes. Another reason, maybe even if you buy such a thermistor from the same manufacturer, from the same batch, you will not have the same steady state characteristics. So the problem of thermistors is that you can't take one sensor, replace that with the same type of sensor without calibrating. So for a thermistor sensor, you need always to calibrate your calibration. That's the biggest advantage of PD model. It's so precise that we don't need any calibration. And now, how to handle the problem of linearity? Well, we know that the sensor has such steady state characteristics, so it's really non-linear thing. If I want to make it appear linear, I can either make it work only in a very small range, which would be this case. And one simple correction where we could use to linearize the dimension is here. I have a temperature sensor, and I know a resistor in series and a resistor in parallel. So, for example, I want to linearize that around 25 centigrades. For 25 centigrades, my resistor has 10 kiloohms. And the best thing is that you choose the same values for the resistor one. Because you have 10 kiloohms, here 10 kiloohms sensor, plus 10 kiloohms you see per day, and here you have 10. So this gives you approximately the same resistance as initial. Not really, because you have 20 kiloohms or by 10, because it's a little bit smaller than approximately. I will go through my simulation. There is a chart that simulates exactly that. You can identify that in this field. Although you just mentioned the difference between the real characteristics and the linearized is really big. So you need to be really close to the 25 centigrades to do some reasonable level. So this is just some simple way of linearized. But today, the best way to use is to use some microcontroller that has a stored table. So you have a table like that in the CPU, and you linearize this chart piecewise, and you say, okay, when I in this region I use some form of equation, when I in this region I use another form of equation, describing the dependence. This is the best way to linearize them. It's clear that I will need some standard signal on the output, and it's clear that this will be much more expensive than if I have just a bridge with 4 resistors or this kind of function. So this is a more expensive way, and then it's up to you. You have a cheap sensor, you have a sensor that you need to calibrate every time, and you have an expensive electronics that you will handle. So that's the thermistor sensor. And last kind of sensors for today will be also built from semiconductors. Semiconductors are good. We have quite a good process to manufacture semiconductor chips. Now, semiconductor sensors will have a limited temperature range. It's the same like for thermistors. The maximum temperature is around 50 centigrades. Semiconductor sensors, they look like that. They again have to be placed typically within a well. So we use that on the glass. Here's an example of a temperature controller that could be used to connect sensors. The advantage of semiconductor sensors when they are made in a special way would be their high sensitivity and nearly linear dependence between temperature and between the electrical resistance. It will be cheaper than RTDs, but they usually have some built-in electronics, and the precision is typically not so good like for RTDs. So again, for a cheap application, choose either a thermistor or a semiconductor temperature sensor. But for an industrial application, you need reliability, accuracy, and robustness, and we need an RTD. So now, what is inside of the sensor? There are two possibilities how you can measure temperature of the semiconductor. A little bit on and two. It's a diode and it will be a transistor. So if you have such a simple connection, you have a diode, and here you have a current source. This current source pushes current through the diode, and you measure the output voltage on the diode. If you would measure the volt ampere characteristics of the dependence of current through the diode on voltage, you would see this. It has the formula there. This is typically 0.5 volts approximately, and it changes with temperature. So if you have temperature T1, is this form characteristic. If you have T2, is this one. And if this is a current source, which is relatively easy to do, let's say I have a constant current, so constant current, and I raise voltage. This gives me voltage for temperature T2. This gives me voltage for temperature T1. So just by measuring the voltage, I can measure the temperature. Of course, I'm limited to some small ranges. Typically, this can work from centigrades. The typical sensitivity of this connection is about 10 millivolts per Kelvin. So it's a small voltage for that small current. The connection is quite easy. Typically, all this is encased inside some chip. Then you have just some three terminals. Looks like that. You have ground, also supply voltage, and the other. So with the diode, it's quite easy. You can do similar thing with a transistor. If you have a transistor in form like that, so base energy conductor, you push the current through this transistor, then the voltage between the base and emitter is a function of temperature. And there is a problem. Equation describing the problem. So we have the current that we are pushing through, and this is IS as a function of temperature. So it's not really a good connection to measure just the current layer, because we will have a dependence of temperature here and temperature there. So what really happens inside the chip is that we compare the two currents. We compare and we measure the difference between the two currents. So here you can see the same thing. Transistor and push it through the current and push it through the current to the second transistor. But there is a difference in this connection. Here, the current goes directly through to resistor R1, but here it goes through resistor R2. So there is a difference in the resistivities. This operation amplifier tries to compensate for this difference. So the output voltage it measures here is a function of temperature. So if you are really interested in some details, then I recommend you take a look at this video. It's really long, it takes about an hour. It's a detailed explanation how what is exactly happening inside. For us, it will be really cool to know, okay, there is a transistor, and explore the changes of transistor current as a function of temperature. It's all going to be. Now, how to use those kind of sensors? You're going to have a simple connection. You're going to have either as a variable resistor or as a voltage source. So this is a typical connection. Here you have this kind of sensor changes its electrical resistivity as a function of temperature, and you connect that as a voltage divider, and you measure the output voltage. It's really easy to do in just two components. The typical characteristic is it's the red line, it's linear, it's quite linear. The blue line is the PTC for comparison, so it's a temperature use. The second connection, if you want the voltage as the output, is to take this sensor, so it same function, changes touch resistance, this changes the voltage. In this case, we have 1 millivolt per calorie minutes and total figure of 1 or 10. Just some units. What is interesting, if you use those kind of sensors, is that you can connect more sensors directly without any additional electronics. You can have information about average temperature or about the minimum temperature and so on. So this is an example of the connection. Here we have 3 sensors. Temperature. I connect them to our. We know that the current is a function of temperature. So here the source current flows here, the source current flows here, the source current flows there. The current will sum up and we will create a voltage drop in this resistor. So the voltage here is proportional to the average current and average temperature measured by those resistors. So if you want to measure temperature in this room, place one sensor here, one sensor in the middle, and one sensor in the back, and it gives you automatically the average temperature. The second connection connects the 3 sensors in series. So the current flowing through those 3 sensors will also be a function of temperature, but this time we will do minimum temperature. Because minimum temperature means minimal electrical resistance and the highest current. So it will add, and here again a resistor where we measure the voltage. To give you an idea about the accuracy of this connection, let's take a look at this chart. Here is temperature from -20 to 100 centigrades. When it is calibrated for 25 centigrades, you know, approximately plus minus 0.5 centigrades of temperature error, so which is much less precise than 1500. Moreover, the error increases with increasing and decreasing temperature. So the higher the temperature or the lower the temperature from 25 get higher. So let's say 100 would give me plus minus 1 centigrades. So they are less precise but less expensive. Applications. Typical application of this semiconductor sensor, they are small, so they can be used to measure temperature distribution. This was an example from Zurich, Switzerland, where they used that to estimate thermal temperature